Alright, welcome to our fourth video. This one's called Electrolytes. So, you don't care. Let's move on. So, an electrolyte is a compound that conducts an electrical current when it's in an aqueous solution. Meaning, you take an electrolyte, dissolve it in water, and you can now conduct electricity with that water. That also means that just pure water does not conduct electricity. Surprise. So if you're getting rained on, you're not going to get electrocuted if it's just rainwater. So, surprise. It's got to have some salt water, like ocean water, or something dissolved in the water that's an electrolyte, will then electrocute you. So don't go standing in water without electrical current at all, but just for trivia, you got to have something dissolved in the water for it to actually conduct electricity. In case you'd like to know, electricity is basically electrons. So you got to have something to give electrons for electricity to move. An electrolyte is a compound that conducts an electrical current when it is in an aqueous solution. Common examples of these are salts, for example, in drinks like Gatorade that say they provide electrolytes. They're often just some kind of salt that's dissolved and really useful for when you've done a workout or just worked really hard for a while and your body has lost some actually salt through sweat. It helps replace that so that your body is able to actually transfer energy amongst itself and help you feel a little bit less tired. Continuing on, all ionic compounds are electrolytes because they dissociate into ions when placed in water. An ionic compound is a compound made up of ions. And so when you're able to place it in water, it just splits back into those ions. For example, a common ionic compound is sodium chloride. Some others are potassium chloride, calcium phosphate, and maybe even sodium hydroxide. Not sure why I put parentheses there. Each of these are named in a very similar way, which helps you know they're ionic compounds. We call this sodium chloride, and the two ions that compose it are sodium and chloride. We have potassium and chloride. We call it potassium chloride. This is calcium and phosphate, so we call it calcium phosphate. This is sodium hydroxide, and so we call it sodium hydroxide. Sodium chloride, when we put it into water, will dissociate into sodium and chloride. For example, let me show you how some of them dissociate. Sodium chloride, when placed in water, will be sodium plus and chloride. This is what we call the sodium ion, and this is the chloride ion. Hopefully you remember this is the element chlorine. However, when it has a 1- charge, we call it chloride. Magnesium hydroxide, from a recent homework, would split into magnesium 2+ and 2 hydroxides. Or calcium phosphate would split into 3 calcium and 2 phosphate. What this actually means is anytime you see the phrase aqueous sodium chloride, what you're actually looking at is sodium and chloride. You won't find NaCl bonded together when you're in water. You'll either find sodium or chloride. For example, same with all these, or any ionic compound. You'll just find the ions, you won't find the compound. This allows for a transfer of electrons because, for example, sodium plus and chloride, the sodium plus means that sodium has lost an electron and given it to chloride. This transfer of electrons is basically the same thing as a transfer of electricity, which is why electrolytes are named for compounds that, when dissolved in water, help transfer electricity. A non-electrolyte is a compound that does not conduct an electric current when it's an aqueous solution. It may dissolve, as in go from a solid to kind of aqueous, but it may not dissociate into actual ions and thus transfer electrons and thus conduct electricity. So electrolytes conduct electricity, non-electrolytes do not. While electrolytes do conduct electricity, not all of them do it to the same proportion. In a solution that contains a strong electrolyte, all or nearly all of the solute exist as ions, meaning all or nearly all of the compound completely dissociate. Every ionic compound, like the ones I showed you before, are strong electrolytes. They will basically dissociate all of it. However, there are other compounds that only dissociate partially. Most soluble salts, like the ones I showed you before, inorganic acids, we'll talk later about organic, but for now, most acids or bases that you know are inorganic. And inorganic bases are strong electrolytes. Most compounds that we've talked about so far in this unit are going to be some kind of strong electrolyte. A weak electrolyte conducts an electric current but weakly, so because only a little bit of the solute in a solution exists as ions. Strong electrolytes, actually let's go back even farther. An electrolyte is a compound that conducts an electric current when dissolved in water. A non-electrolyte does not at all. It may dissolve, but it will not dissociate into ions, which means it will not conduct an electric current. A strong electrolyte dissociates all or nearly all of itself, but a weak electrolyte will only do part of it. It still will conduct an electric current, but not very strongly. Only some of it will dissociate, which means that some of it will remain undissociated. Organic acids and bases are very common examples of weak electrolytes. Or we'll talk about weak acids or weak bases later on. An organic acid typically is something that looks like this. It's a compound consisted mainly of carbons, hydrogens, and oxygens. You won't see sodium or chloride. You'll basically just see only these compounds. Typically, those are going to be organic acids or bases. This is not in your notes, but I'm going to give you a little bit to start writing this down on the side of your notes. This is a very useful categorization for electrolytes. And your objective for this section is you can basically tell me whether a compound is a strong electrolyte, a weak electrolyte, or a non-electrolyte. So I'll give you a few minutes, write this down, and then we'll start talking about it. Hopefully you've had enough time to actually write down this chart. I'm going to talk you through it, show you an example or so, and then you get to practice some of this. On the test, by the way, this is probably the main question you're going to ask. I will not be giving you this chart. However, I will be giving you, if you're in general, a list of strong acids and strong bases. Honors, sorry, you get to memorize them, but we'll talk about those later. So, the way this is it's almost a flow chart, if you will, for compounds. You take whatever compound you're dealing with and you go step by step. And whatever compound you're dealing with will apply to one of these. So, first off, you determine if it's a strong acid. If it is, you're done, and we'll come back to that later. If it's not a strong acid, you see if it's a strong base. And if it is, you're done, and we'll come back to it later. If not, you want to see if it looks like a metal to some number or a non-metal to some number. For example, sodium, chloride, or calcium, fluoride. Both of those are a metal and a non-metal. In this case, sodium chloride is actually Na1CO1, Ca1F2. These A and B's represent the actual subscripts. If it looks like this, then we're going to call it a salt. And we'll come back to that later. Alright, so again, if it's a strong acid, cool. If not, maybe it's a weak acid. If not, maybe it's a metal and a non-metal, so we call it a salt. If that's not true, if the formula starts with an H, then it's probably a weak acid. That's why I got the little ish sign. This is most of the time true, and I'll admit there's not all the time. This is not going to work for all the time, but unfortunately I can't give you a better way to do that. A lot of these are going to come from memorization, but most of the time it will be a weak acid if it starts with an H. Okay? If it's not a weak acid, maybe a nitrogen is somewhere in the formula. If that's true, then it's probably a weak base. Very common one, NH3. And actually a very common one for weak acid could be HF. It's actually not a strong acid, but it does start with an H. If none of these are true, then we're going to assume it's a non-electrolyte. So, if it's a strong acid, cool. If not, maybe it's a strong base. If not, maybe it's a salt. If not, maybe it's a weak acid. And if not, maybe it's a weak base. If none of those are true, it's a non-electrolyte. Hopefully you notice, but that if it's a strong acid, or a strong base, or a salt, then it's a strong electrolyte. If it's a weak acid or a weak base, then it's a weak electrolyte. So that means sodium chloride is a strong electrolyte. Calcium fluoride is a strong electrolyte. Hydrofluoric acid is a weak electrolyte. Ammonia is a weak electrolyte. And if I gave you something else, probably be a non-electrolyte. Alright. So with that, go ahead and try and classify these compounds. There should be a list on the board of these strong acids, strong bases. If not, just remind me and I'll put them up for you for now. Good luck. Okay, welcome back. So with this first one, hopefully you realize it's not a strong acid or a strong base. Doesn't start with H. Doesn't have a nitrogen in there. So this is going to be a non-electrolyte. I'm sorry, and it's not a salt either. Potassium chloride is a metal and a non-metal. So we're going to call it a salt, which means a strong electrolyte. I2 is basically none of the above, so that is a non-electrolyte. Now, magnesium sulfate's a little interesting because it doesn't actually fit with a lot of the things I told you up there. However, magnesium sulfate is what we call an ionic compound. Most of the time when you look at a salt, it'll be one metal and one non-metal. However, what that should have actually been changed to is one metal and a couple non-metals, which fits with magnesium sulfate. This will be a salt. And NaHCO3 is also actually a metal and some non-metals. This will be a salt, which is a strong electrolyte and a strong electrolyte. What wouldn't hurt is to go back and put metal A, non-metals to some B. Hopefully that'll be good enough. Thanks for watching. Hopefully this helped.